Hi everyone, this is Srikanth, Assistant Professor of Data Science Department. In this session, I am going to discuss about transportation problem in the optimization techniques. So after completion of this particular transportation problem, we can apply the optimization techniques in order to find the initial basic feasible solutions and move towards optimality in the transportation problems, including unbalanced and maximization cases. In operations research, linear programming is one of the model in mathematical programming, which is very broad and vast. The mathematical programming includes many more optimization models known as nonlinear programming, stochastic programming, integer programming, and dynamic programming. Each one of them is an efficient optimization techniques in order to solve the problem. So here we are having different mathematical programming models are there in order to optimize our problems. So in that, the first one which we have covered is linear programming problem, and the next models are nonlinear programming models and stochastic programming models and integer programming and also dynamic programming models. So what is transportation problem? Okay, first we can remember that the general linear programming model is based on the assumptions. The first one is certainty and the next one is linearity. So we have taken in the linear programming problem, we have taken certain assumptions. In that, the first one is certainty. So the resources available and the requirement of resources by completing candidates, the profit coefficients of each variable are assumed to remain unchanged and they are certain in nature. So in the linear programming, we have taken the resources available and the requirement of resources by competing candidates, and the profit coefficients of each variable are assumed and these are remain unchanged and they are certain in nature, they can change. And linearity, the objective function and structural constraints should be linear. We have assumed all the constraints and objective functions are assumed as linear. And the next one is divisibility. All variables are assumed to be continuous. Hence, they assume integer or fractional values. We have considered all the variables are assumed to be continuous. Hence, they can assume integer or fractional values. And the next one is single stage. The model is static and constrained to one decision only. Here, in this particular linear programming, the model is static and constrained to only one decision. So the planning period is assumed to be fixed. Here the planning period is assumed to be fixed. And the next one is non-negativity. We have considered all the constraints or constraints variables must be greater than or equals to 0. So that is also one of the assumptions we have taken. A non-negativity constraint exists in the problem so that the values of all variables are to be greater than or equals to 0. The lower limit is 0 and the upper limit may be any positive number. In this, we have considered the lower limit for the constraint is 0 and the upper limit may be any positive number. And the next one is fixed technology. The production requirements are assumed to be fixed during the planning period. So production requirements are also assumed, that is the number of hours which can work, all these are assumed to be fixed during the planning period. And constant profit or cost per unit. So here we have taken a constant profit which we have taken, or cost per unit also constant we have considered, because these are the values which we are considering for preparing our objective function. These values we are considering as the constant. Now let us examine the applicability of linear programming model for transportation and assignment models. The transportation model deals with a special class of linear programming problem, in which the transportation model deals with a special class of linear programming problem in which the objective is to transport a homogeneous commodity from various origins or factories to different destinations or markets at a total minimum cost. So the name itself says transportation. So we need to transport the products from the manufacturing unit or from the industry to all other marketplaces that where there is a demand for the products. So with a minimum cost, we have to reduce our transportation cost. So that is our transportation model. This is going to be a special class of linear programming problem. From various origins to different destinations or markets at a total minimum cost we need to transport. And to understand the problem more clearly, let us take an example and discuss the rationale of transportation problem. So in order to understand clearly, let us take the example. So in the example, we are considering three factories. A, B, C are going to manufacture sugar and are located in different regions. A, B, C are the factories we are considering, and these factories are going to manufacture the sugar and are located at different regions. And factory A manufactures B1 tons of sugar per year. Factory A is going to manufacture the number of tons per year are B1, and factory B manufactures B2 tons of sugar per year, and factory C is going to manufacture B3 tons of sugar. The sugar is required by 4 markets. So these are the demands. Okay, from the markets, what are the demands are there? Those we are considering there are 4 markets: W, X, Y and Z. So these are the 4 markets we are considering. The requirement of the 4 markets is as follows. The demand for sugar markets W, X, Y, Z is D1 and W respectively D1, D2, D3 and D4 tons respectively. So in the transportation problem, we are considering 3 factories A, B, C, and each factory are going to manufacture B1, B2, B3 tons of sugars, and the markets we are considering as W, X, Y and Z, 4 markets we are considering, and all these 4 markets are having several demands like D1, D2, D3 and D4 tons respectively. And the transportation cost of 1 ton of sugar from each factory to market is given in the matrix below. So the transportation cost is given below. We need to reduce the transportation cost. The objective is to transport sugar from factories to the markets at a minimum total transportation cost. So here is the transportation model. So here the factories and demand in tons, factories and demand in tons A, B, C, and from W for marketing from A to W, the cost which is transportation cost is C11. From A to X, the transportation cost is C12. A to Y, transportation cost is C13, and A to Z, the transportation cost is C14, and the availability in tons is number of tons available from number of tons manufactured by factory A is B1. Okay, so in the same way, from B2W, C21 is the cost of transportation, from B2X, C22, from B2Y, C23, from B2Z, C24, and from C2W, C31, from C2X, C32, from C2Y, C33, from C2Z, C34. And these C11, C21, C31, and these are the transportation cost from the three factories to W. So we have to choose the minimum value in order to reduce our transportation cost. So these are the demands D1, D2, D3 and D4. Here availability in tons is summation of Bj by summation of Dj. Here is the, for the given data, the mathematical model will be, we need to minimize our cost. That is, Z is equals to C11 in C11 X11, C12 X12, C13 X13, C14 X14. Like that, we need to take C21 X21, C22 X23 up to C34 and X34. Subject to a condition, this is our objective function. And the constraints are, we need to consider A11 X11 plus A12 X12 plus A13 X13 plus A14 X14, which is less than or equals to B1. And A21 X21 plus A22 X22 plus A23 X23 plus A24 X24, which is less than or equals to B2. And in the same way, A31 X31 plus A32 X32, A33 X33, A34 X34, which is less than or equals to B3. These are the mixed structural constraints. And the next constraint is A11 X11, A21 X21, A31 X31, which should be greater than or equals to the demand D1. A12 X12, A22 X22, A33 X32, which is greater than or equals to D2. In the same way, for the D3 and D4, we have to write the constraints, because here the sum must be greater than or equals to the demand of market. We cannot send the less than what is required. So here all Xij and Xji are greater than or equals to 0. We are considering non-negative constraint because we cannot supply negative elements. So where I is equals to 1, 2, 3 and j is equals to 1, 2, 3, 4. And this is the non-negativity constraint. So the above problem has got the following properties. It has an objective function as like in the linear programming problem, and it has structural constraints. It has structural constraints, and it has a non-negativity constraint. Non-negativity constraint, and the relationship between the variables and the constraints are linear. So here we have got 4 properties. One is it has an objective function, it has a structural constraints, it has a non-negativity constraint, the relationship between the variables and the constraints are linear. So we know very well that these are the properties of linear programming problem. Hence the transportation model is also a linear programming problem, but a special type of linear programming problem. These are the references I have considered for this particular topic. Operations Research, an introduction, Hamdi A. Taha, PSN Education, an introduction to Operations Research, Frederick S. Hellier and Gerald J. Lieberman. McGraw Hill Education, and Operations Research SD Sharma, Kedarnath, Ramnath, and O. And web references Khan Academy, Geeks for Geeks, and tutorialpoints.com. In this session, I have discussed what is transportation problem and when to use and what are the steps involved in the transportation problem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.